In the last class, we started discussing parallel transport. And so let me just do a quick recap of that. Mm, Just a second. Hey, sorry, just give me a minute. Hello. Hello.
Yes, sir.
Sorry, there's some weird interruption for which I had to kind of urgently do something. Uh, okay, so let's come back to this parallel transport thing that we were discussing last time. And what we said was that if you are in the Euclidean space, then we have some notion of parallel lines, parallel vectors, and so on. And they are defined by writing the vectors in the component form and saying that the ratios of the components along uh, any specific unit direction uh, are same. So ax by bx is equal to ay by by kind of stuff, which is the definition of what we would call parallel vectors. Okay. Problem, of course, was that this notion doesn't generalize to curved space, simply because in the curved space, the vector is defined only at a particular point. Okay, so until you transport a vector defined at any other point to a vector defined at that point, you cannot really say whether the vector is parallel or not. Okay. So okay, so therefore we wanted to kind of define a notion of how to transport a vector. So far we have defined only vectors at a particular point. Now we want to transport a vector from a place to another place and compare the vector defined at another point. Okay, and that's where this concept called parallel transport gets in. Okay, so that's what we had started looking at. Okay, so we said that, like, if you want to do a parallel transport of a generic tensor, vector is like one rank 1 tensor, so we might as well ask this question for arbitrary tensor. So we wanted to ask a question that how do we transport a tensor along a curve? And as I said last time, that the parallel transport in the curved space depends on the path that you use. Okay, so along different paths, the uh, tensor would get parallelly transported in a different way. And so if you parameterize the curve using lambda, then you can ask how does the tensor change as you change lambda. That means as you go from one point on the curve to another point. And that is given by dt by d lambda, which by using chain rule you can write in terms of dx by d lambda times the partial derivative of t. Okay, and you say that a vector is parallelly transported if it is held constant all along the process, and that would mean that dt by d lambda should be 0. Okay, but the problem with this expression is that this derivative of tensor is not a tensor quantity, and as a result this equation really does not have any invariant meaning, simply because in some coordinate system this would be 0, in some other coordinate system it would be non-zero. So what we want to do is to actually define, yeah, this was just a figure to just explain what parallel transport was. So what we wanted to define was a covariant derivative along the path, and that we called capital D by d lambda, and that would replace the partial derivative by the covariant derivative. Okay, and if you do that, then of course the covariant derivative of the tensor along the curve would give you the tangent vector to the curve times the covariant derivative of the tensor equal to 0. And this is of course a tensorial equation, and therefore would make sense in every coordinate system. So if you obtain a solution in one, you know that that is going to be true in all other coordinate systems. Okay, so that was the reason for introducing this quantity. Okay, fine. So now let's kind of ask this question, go back to the vector case, and you replace t by a vector, contravariant vector, then you get an equation which is dx sigma by d lambda times the covariant derivative of the vector, which is partial derivative of the vector plus gamma sigma alpha beta v beta, and that should be equal to 0. Okay, so that is the kind of equation. Now given that the tangent vector at any given point is typically is non-zero unless the space of course degenerates, we are looking at spaces which are non-degenerate spaces. That means the metric is well behaved everywhere. Okay, uh, in that case of course this is non-zero, implies that the quantity inside the parenthesis should vanish. Okay, so this is the equation for parallel transport of a vector. Okay, and as we already said that it depends on a choice of path as well as choice of connection. And the choice of connection of course is not something we are going to worry about too much, because we are not going to look at metric non-compatible connections in this course at all. But I just mentioned this just to kind of let you know that you could write down connections which are not metric compatible, and in that case of course you need to be a little more careful. Your space may have torsion, and in that case you need to take a torsion tensor into account. Okay, fine. So good. So if the connection is metric compatible, then of course this parallel transport of the metric itself would vanish, simply because the covariant derivative along the curve would correspond to covariant derivative of the metric, and we know that the metric is supposed to be covariantly constant with respect to Riemann-Christoffel connection. Okay, and therefore this tells us that the metric, the parallel transport of the metric along a curve would just vanish. Okay, fine. So of course, the next question was that we took a step from d by d lambda to capital D by d lambda thing, which is what is called the covariantization. Okay, and the question, of course, would be how do we know that this covariantization corresponds to parallel transport? Okay, so for that, let's consider two vectors, one defined at x naught and the other defined at x naught plus delta x naught, so a small distance away. Okay, uh, and uh, uh, and let's consider a coordinate system which is such that the gamma would vanish in the x prime coordinate system. Okay, so these are defined in x coordinate system. We choose a x prime coordinate system in which gamma is 0. Okay, in this coordinate system, of course, v would go to v prime and w would go to w prime. Okay, and we want to ask, how do we kind of study relation between v and w? Okay, so the statement is that v and w are related by parallel transport if v alpha prime is equal to w alpha prime up to corrections of order delta x naught squared. Okay, so that means there is no correction to a linear order, but at quadratic order. Okay, that is the thing. Okay, so let's write down the vectors in the unprimed coordinate system. They are related to these vectors in the primed coordinate system through this coordinate transformation. Similarly for W, except that this derivative is evaluated at x naught prime, whereas this is at x naught prime plus delta x naught prime. So we can do a Taylor expansion of this around this to kind of write down the terms. Okay, we want to know what is the difference between these two vectors. Okay, so that is just substituting the expressions, del x alpha by del x prime alpha prime, once at x naught plus delta x naught prime, and once at x naught prime plus delta x naught prime. Okay, now remember, in the prime frame, we to leading order, we are choosing them to be same up to a correction which is at quadratic order. So to leading order, they would be same. Okay, and as I said, we would take this piece and do a Taylor expansion of this around x naught prime. So that would be del x alpha by del x prime alpha prime at x naught prime plus delta x naught prime is equal to del x alpha by del x alpha prime at x naught prime plus the second derivative piece. Okay, which is the next piece in the Taylor expansion. So which is the second derivative with respect to del x. I should have put del x prime beta prime. Prime is missing here, but yeah, that's what it is. Yes. Any question? Okay, if not, let's continue. So what we'll do is we'll take this expression and put it back in and use the fact that to leading order v prime is equal to w prime, and if you do that, then we get the equation where the leading piece will just cancel out, because remember, just let's go a step up. Yeah, once you expand this term is same as this term. So you can pull it out, and then you get V alpha prime minus W alpha prime, which are also equal to leading order. So that first derivative piece just cancels. The next, excuse me, next piece is a second derivative piece, and that is the piece which will remain. Okay, and what we will do is basically write down that expression. Okay, fine. We have used the fact that W alpha prime to leading order is same as V alpha prime here. Okay, so so this is what we would get by actually looking at the difference of two vectors in the unprimed coordinate system. Okay, fine. So but remember that, like, we are working in the primed coordinate system in which the connection was 0, right? That is what we were working with. Let me just step back. Right, in the prime coordinate system the connection was 0, but the connection in the unprimed coordinate system is related to this fellow by coordinate transformation. Okay, that coordinate transformation would be exactly this piece, that del x by del x prime with indices beta and beta prime, gamma and gamma prime, and of course alpha prime and alpha also is plus this piece is equal to 0. Okay, so I am using this fact that the 0 which is on the right hand side is actually gamma alpha prime beta prime gamma prime piece. Since that piece is 0, I set this term is equal to minus of that term. Okay, so what we'll do is we'll replace this term by del x beta by del x beta prime, del x gamma by del x gamma prime times gamma. Okay, and a minus sign, of course. Okay, so if you put that back, you get an expression which is like this. Okay, does that make sense? Okay, so at this point, what we could do is we can use del x beta by del x prime beta prime and delta x beta prime should have been x prime beta prime, as I said. You can take them together to use vector property to write this as delta x beta, and similarly use this with v gamma prime to write down v gamma. Okay, so therefore just using the vectorial transformation properties of these two quantities, you can write down v alpha minus w alpha is equal to gamma alpha beta gamma times delta x beta v gamma. Okay, so are you with me with this manipulation? Any questions at this point? Okay, if not, let's go ahead. Uh, so, so what we'll do is we'll define this thing v alpha minus w alpha to be a small variation in v alpha. Okay, so let's call it minus delta v alpha. Okay, and if you do that, then this expression, sorry, this equation can be written as delta v alpha plus gamma times delta x beta delta v gamma equals 0. Okay, and which would imply that dv by d lambda plus gamma times del x by del sorry, it should have been dx by d lambda times v gamma should be equal to 0. Okay, that's precisely the parallel transport equation that we had derived. Okay, so if although we naively got the partial derivative, if you actually did a careful calculation, you would find that the next order correction that we should have taken into account, which is the second derivative piece, if you did take that into account, then the equation is actually a covariant derivative equation and not the partial derivative. So the partial derivative equation that we had written down initially was too naive. It would have worked in the flat space, but not in the curved space. Okay, fine. Any questions at this point? Okay, so let's go to the next step, and that is that parallel transport actually preserves the inner product between vectors. So if you have two vectors defined at a particular point, you define their dot product, okay, and then you parallelly transport these vectors along a particular curve. Of course, both are transformed along the same curve, okay, and you go to the new point, okay, then their product, the dot product would be same. Okay, now to see that, what we need to check is what is the change in the dot product as you parallelly transport this, the scalar product. Okay, so that is given by the covariant derivative with respect to the parameter which defines the curve. Okay, g alpha beta v alpha w beta is the inner product between v and w. Okay, and now you can just push it through and write it in terms of parallel transport operator acting, I shouldn't use the word parallel transport operator, the covariant derivative along the path acting on individual quantities. So once it acts on g alpha beta, once on v, and once on w. Okay, but of course g alpha beta is not parallelly transported. Okay, so therefore this just vanishes, and these two terms are the ones which are parallel transport equations, and therefore they vanish individually. I mean, there is no cancellation between this term and that term, but they individually are zero, and therefore it tells you that the variation in the inner product of two vectors defined at a particular point, as you parallelly transport the vector, both vectors along the same curve, is zero. Okay, so inner product is preserved along the parallel as you do the parallel transport. Okay, so is this okay? Okay, so good. So of course we have used the fact that this path covariant derivative contains the connection which is metric compatible to set this quantity to zero. So therefore we kind of conclude that the metric compatible connection preserves the norm of the vector. Okay. So here's a small exercise. You can show that the parallel transport equation is invariant under a coordinate transformation. Okay, it's kind of trivial given the fact that like we have written that equation in the tensorial form, but nevertheless it may be worth it. Okay. Okay. Now, first thing is that the rule of parallel transport is linear. Okay, so that is one important thing. It does not, I mean, given a vector, the parallel transport equation is linear in the vector. It is not any higher order, or it doesn't contain fractional power. In that sense, the rule is linear. Okay, so therefore, because the fact that the parallel transport is linear, if you are given two vectors, V alpha and a W alpha, and if they both satisfy parallel transport equation, then any linear combination of V and W would satisfy the parallel transport equation. Okay, that is typically what happens if you have linear equations. Is it okay? This is something we have seen in quantum mechanics, for example, that you can write down linear superpositions of states and so on, simply because Schrodinger equation is a linear equation in the wave function. Okay, is it fine? Okay. Okay, so let's consider a vector V alpha defined at lambda 0, where lambda 0 is a affine parameter corresponding to some initial point at which the vector is defined, and let lambda be a final point where you would want to transport the vector V alpha uh, along a particular curve. Okay, fine. So a curve is of course parameterized by lambda, whose lambda 0 value is a place where the vector is defined, and lambda is a value at which you want to ask how the vector looks like. Okay. So what we'll do is we'll introduce a new object called a parallel propagator, which is defined as P alpha beta lambda lambda 0, which has the following job, that it picks up a vector defined at its second argument and drops it at its first argument. Okay, so it has action on the vectors which are defined with second argument. In this case, it should be V of lambda naught. Okay, and the end result of its operation would give you V at lambda. Okay, now of course we know what this would be. Okay, uh, that it has to be some kind of a form of the parallel transport equation that we have. But remember, parallel transport equation is a differential equation, right? It's a derivative acting on V plus some gamma times V kind of equation. Whereas, so, but derivative is of course defined in the limiting case, right? That x plus delta x minus x kind of thing. So therefore, differential equation will tell you only local information. It will just transport you a infinitesimal distance. Whereas what you want to do here is to do a finite transformation. So in some sense, you want to integrate the uh, parallel transport equation to arrive at the answer which is given here. Okay. So what we will do is we define a quantity A. Okay, just to simplify our calculation, uh, we could have carried these two terms all through our calculations instead of defining A, but it is just convenient to use quantity A so that the equation doesn't look too cluttered. Okay. Of course, at the end of the computation, we would of course substitute that as minus gamma alpha beta gamma times del x gamma by del lambda. Okay, but right now we'll use A alpha beta. Okay. So put it back, use this in the parallel transport equation, and the parallel transport equation would take the form like this. Okay, this minus sign is chosen deliberately so that you push A on the right hand side and not carry a minus sign. Okay, nothing very special about it otherwise. Okay, fine. So what we want to do is to actually solve this differential equation. Okay, but this differential equation has a problem, well, not problem, but has a property that you have a v lambda sitting here, v lambda sitting here also, but uh, if you try to kind of bring v lambda down and try to do an integration, then the problem is that that v is also a function of lambda. So therefore, when you do a lambda integration on the other side, you cannot take v out of that integral. Okay, so therefore, it is not like you write down dv by v and integrate and say that is log v, and you do a integral a lambda d lambda and just write that integral quantity. Although eventually the quantity is going to look similar, but uh, what you really need to do is to do a careful calculation uh, of of this equation to arrive at the solution. So what we'll do is we will remember parallel transport is always done infinitesimally using the differential equation. We would find solutions which are infinitesimally away from the initial value, take that solution, put it back, compute it again, get the solution which is further infinitesimally transformed, put it back, and so on. It's some kind of iterative way of solving it. Okay. So what we will do is the following. Okay. Uh, we will use the the parallel propagator uh, to write down v alpha in terms of v alpha lambda in terms of v alpha lambda naught. Okay. Once you do that, then this entire differential equation actually shifts to a differential equation acting on the parallel propagator. Okay, because both of the sides would have v alpha lambda naught, which is not a function of lambda, so d by d lambda is not going to act on it, and there are so v alpha or v beta lambda not sitting around there as a spectator, and you can just cancel that piece out. Okay, so we have transferred this to an equation satisfied by with the parallel propagator. Is this okay?
So what is a spectator? I will.
Oh, by spectator, I mean nothing is acting on it. I mean, v alpha lambda naught is just a constant quantity. So d by d lambda doesn't act on it because it's not a function of lambda,
Oh
right?
yeah. Yes,
And on
yes.
the right hand side also, if you write a propagator times v alpha bit or v whatever some variable times uh, uh, lambda naught, then that also is just sitting around. So you can just cancel from both sides. That's what I mean by spectator. In the sense, it is not involved in solving the equation.
Okay.
Okay. So now what we want to do is to actually solve this equation. Okay. So what we'll do is we will do this integration uh, and the integration will be written in this particular form. Uh, okay. And of course, we'll have to do it iteratively. So first thing that we need to do is to fix this quantity. Now this is in some sense constant of integration, but it is important. It is important simply because if you do not parallelly transport the vector at all, that means if lambda is equal to lambda naught, then you should get your vector back. Okay, because you're not really doing anything. You're not moving the vector along anything. Okay, so that should give you vector back. Okay, and that tells you that if this integral is from lambda naught to lambda naught, which would just mean that when this integral just vanishes, okay, the in that case p should be just 1. Okay, so that is the boundary condition that the parallel propagator has to satisfy. Modulo that boundary condition, what we are trying to do is to just write down a formal solution such that if you differentiate on both sides, then left hand side will give you d by d lambda of p, and right hand side will just get rid of this integral and the d tau p's and replace tau by lambda. Okay, which is what will give you this equation. Okay, so this is like a formal solution, because when you take d by d lambda, of course this delta alpha beta would just vanish. Okay, now of course we want to ask, how do we actually solve this integral? That is where the whole game is. Okay, fine. So this is something I just explained, that this is necessary for correct normalization at lambda equals lambda naught. Okay, so what we will do is basically solve these things recursively. That means whatever p which appears here, we will just substitute this form of p inside there. Okay, so it's kind of a self-consistent or recursive way of solving the equation. Okay, so that's what we'll do. So, so what we get is p alpha beta lambda naught. The boundary condition is lambda alpha delta alpha beta plus this quantity. Now remember, our initial term was a times p, but now I don't have p at all. The reason why I don't have p at all is, okay, the reason why I don't have p at all is because to leading order I am substituting p as delta. Okay, so let me just keep that equation in front so that, okay, so here's the equation. So and the equation that we wanted to kind of uh, uh, solve was precisely this, but to leading order, so this will be done order by order. So at this place we will substitute delta plus this integral. Okay, so the leading order term is delta, so that just replaces gamma by beta, which is what you get. And the next term is plus double integral, because originally there is one integral and this p is replaced by this entire expression, so you have a double integral a times a times p. Okay, so that is this term. Okay, now you would see that, like, it is a times a, but there is no p here. Well, there is no p here simply because to that order the leading order term is again delta, and that is why I write that quantity. I just replace this variable, which would have been probably delta, by beta. Okay, and we get this expression, and you just continue doing it ad infinitum. Okay, the nth term would look something like this. Okay, so alpha alpha 1, alpha 1 alpha 2 dot, 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 alpha and beta, and then integrate over n such variables. Okay, tau n minus 1 dot, 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 tau 1. Okay, mm, so, and notice that these integrals are done in a particular order. For example, tau prime integral is done from lambda naught to tau, and tau integral is done from lambda naught to lambda. Okay, if you try to look at the nth fellow, it goes like that. Tau 1 goes up to tau 2, tau 2 goes up to tau 3, tau n goes tau n minus 2 goes to tau n minus 1, and similarly tau n minus 1 goes up to tau, and tau actually integrates over the whole region. Okay, so that is the kind of uh, integration that you would get. You would encounter similar expressions when you do quantum field theory. You will notice that, like, if you um, look at how this integration is done over two parameter space, forget about this n parameter space, just look at this two parameter space thing, then you will find that tau prime is always less than tau. Okay, so therefore in the tau prime space you will have to draw a line, uh, consider a square, uh, where the value let's say lambda naught is just 0, just for the argument's sake, then you draw a square whose which starts from origin in tau tau prime space, goes up to lambda in one direction, lambda in another direction, and fourth corner of the square would be a coordinate lambda lambda. Now you draw a diagonal from 0 0 to lambda lambda, and depending upon which one is tau and which one is tau prime, whether x or y axis, either you take the upper triangular part or the lower triangular part of this integration, because tau prime is less than tau. Okay, so therefore if your tau prime is along uh, the real axis, then you will take the upper triangular part. If it is along the by real axis means along x axis. If it is if tau prime is y axis, then you will take the lower triangular part of the square. Okay, so what it tells us is that you are actually integrating over half the square that you really wanted to integrate. Okay, but it would have been much nicer if you had this integral done irrespective of uh, I mean, what is the kind of constraint coming from this? If we could do this integral from 0 to lambda and other integral also 0 to lambda. And the answer is that, like, yes, of course we could do that. And all you need to do is to put a factor of half outside out here. Okay. And in fact, if you do it for the nth order term, then you don't need to put a factor of 1 over n, but you need to put a factor of 1 over n factorial. Okay. So that is the thing. You may even learn it in quantum field theory course because it's kind of essential. Okay. But anyway, so the nth order term has a property that the tau parameters are ordered in particular fashion, which is what I meant by saying that they occupy, they uh, span only half the space, which would have been allowed if you take two parameters. If you take n parameters, then it spans only 1 over n factorial part of the total space. Okay, so so what we will do is that we would use this fact, okay, to ensure that there is a specific ordering. Okay, we define something called the path ordering. Okay, so path ordering would tell you that all all these functions which are written in here, okay, follow a specific ordering. Okay, if you do that, then you could write down these integrals from any value to any, I mean, without putting these restrictions. Okay, that is what the path ordering will take care of. Okay, so path ordering has an advantage that if any one of these variables, say if you find tau n minus 1 actually greater than tau n, okay, then the path ordering operator will automatically take care of it. You don't have to kind of explicitly take care of that. Okay, that is the process that a path ordering would do. Okay, this is pretty much the kind of stuff that you would do, say, when you do path integral in, say, quantum mechanics. Okay, where the quantity that you write inside the path integral, you don't really worry about how it is ordered. The path integral will take care of its ordering. Okay, so this is pretty much like that. Okay, so but once the path ordering operator is going to take care of the ordering of all these quantities, you could write down all these integrals going from lambda naught to lambda unrestricted. Okay, but of course if you do that, you'll have to put a factor of 1 or n factorial in the denominator to soak up for the fact that this whole integral would have given you much larger number. Okay, like for example in tau and tau prime case, it would have given the answer twice as much. Okay, so you put a factor of half in this particular, or rather I should say you should put a factor of 1 over 2 factorial. Okay, although 1 over 2 factorial is same as half. Okay, fine. So what we'll do is we'll take this expression and put it back in this for every term. Okay, so that would tell us that the solution can be written. Remember, like once you put a 1 over n factorial piece, then for any nth term, it is a to the n with n integrals divided by n factorial. So that's almost like an exponential function, or in fact, it is an exponential function, but path ordered. Okay, so what you need to show or see after doing that manipulation, that p lambda lambda naught is actually path ordering of an exponential lambda naught to lambda of a of tau d tau. Okay, that is the expression. If you do a series expansion of this, you will see every individual term coming out of this series expansion. Now we can substitute what a of tau was, which was minus gamma times dx gamma by d tau. Okay, so therefore our parallel propagator takes this particular form. Okay, any questions at this point? Okay, so let's proceed. Uh, so uh, Fine. So instead of like transporting a vector from one point to another point, we could ask, what if we consider a closed loop? Okay. So if the path is a closed loop, okay, then what we would get is that the parallel propagator would basically bring the vector back as you go from lambda naught to lambda. Okay. Now, lambda is of course a parameter which parameterizes the curve. Okay, so therefore that quantity is still going to change, but in the physical space time, you are back to the same point. Okay, so therefore the new vector that you get, okay, is a vector in the same tangent space. Okay, now if you have two vectors defined in the same tangent space, then they can be related to each other by the local symmetry, and the local symmetry that we have is the local Lorentz symmetry. Okay, because locally we can, using equivalence principle, you can say that locally you can always convert the space to be flat. Okay, and if this look, if you have locally Minkowski space, then the symmetry of that space is Lorentz symmetry, and therefore if you have two vectors, you could kind of relate those two vectors by doing local Lorentz transformations. Okay, so therefore the transformation between these two vectors should be related by some matrix which is uh, with constant entries. And remember, Lorentz transformations are done by using matrices with constant entries. Okay, and that is the only one which will locally preserve the metric and relate two vectors uh, in the same frame. Okay, fine. That matrix that we would get, okay, that is typically called the holonomy of the loop. Okay, now remember, we are not just sitting at the same point. We are taking the vector, transporting along a closed loop, okay, coming back to the same point. Okay, so because the loop is closed, obviously. Okay, so so the vector that you get at the end of this transport, okay, is pointing in a different direction in general. Okay, of course, if you are in a flat space, it would be pointing in the same direction. But if you are in a generic curved space, the new vector could be pointing in different direction. Okay, so we want to ask a question: what transformation that you need to do to bring this vector back to the vector that we started off with? Okay, that matrix is the one which is called the holonomy of the loop. Okay, is that okay? Is this obvious, or well, I would have thought that this was not quite obvious thing, but maybe it is easy. Okay. Anyway, so coming back to what I was talking, this thing that when you bring the vector back to the original point, okay, uh, it is not necessary that you may need the entire Lorentz group to do the to rotate the vector back to its original point. Okay. Now, uh, of course, If you choose a specific loop, then it would require only a particular element of the Lorentz group. But the statement is not that. Statement is that you choose any loop, okay, which brings the vector back, and you want to ask a question: what is the transformation that is required? Okay, so for some loop you may just require rotation in xy plane. For some other loop you may require rotation in xy as well as yz plane. Uh, in some third case you may need to kind of do a boost also, whatever. Okay, but it is not necessary that you have a space where you choose arbitrary loop starting from a fixed point. Okay, these are called um, you know loops with a base point. Okay, so you draw arbitrary loops with base point, and you kind of parallel transport a vector and bring it back. uh, you parallel transport and bring it back, then it may happen that the matrix that is required is not the full Lorentz group matrix, but something which is smaller than that. Okay, such a thing could happen. If that happens, then you have curved space with some additional properties, and such spaces are interesting both physically as well as uh, mathematically, actually. Okay, so mathematicians of course would be interested in that, but even in physics you find spaces where the holonomy element does not sit in entire Lorentz group but in subgroup of Lorentz group, and those could be uh, relevant. Okay, uh, fine. So in some sense, the statement about holonomy is quite non-obvious, but nevertheless,
So,
yeah.
are we changing the norm along the direction, like while parallel transporting?
No.
So we don't need the boosts, right? When we try to align it back, because the boosts would only change the length of the vector, not
Yeah, yeah, I agree.
so like for
Yeah, yeah.
we
So I really,
dimensional rotation.
that is right. I really did not mean boost in that sense. Uh, typically, what have okay. So let me step back. Actually, typically holonomies become more important if you are looking at curved Euclidean spaces. Okay, and then you do a Lorentzian rotation by at the end of your calculation. So many of these gravity computations are done in Euclidean gravity, and you do kind of what is called a Wick rotation to go back to the Lorentzian space. So in that case, the geometry is Euclidean, and then the holonomy corresponds to all direction rotations actually locally. Okay, uh, so in the Lorentz transformation case, you may not require all of that. You may require only the spatial thing. Basically, you need to ensure that the norm is not changing. Okay, although local Lorentz transformation, even if you do a boost, the norm wouldn't change really. Okay, because it's a local transformation. Locally, it is still orthogonal group. Okay.
Also, since you mentioned this Wick's rotation,
Yeah.
will it come up in this course?
No, no, no. I am doing classical gravity, so I wouldn't really require doing that. But you'll have to do this in quantum field theory. A lot of quantum field theory computations are done using Euclidean kind of formulation, and then you kind of Wick rotate it back to Lorentzian theory. So uh, it is it is possible that in QFT1 you may not do it, because QFT1 is a operator formulation, and in the operator formulation you define uh, in everything in using Hamiltonian setup, and therefore it's natural to kind of write down spatial thing and time evolution. But when you do QFT2, where you do path integral in quantum field theory, then it is much better to use Euclidean formulation to do all the computation. And at the end of the computation, you kind of do a rotation back to the Lorentzian space. Okay.
Is this mechanics consistent?
It is consistent. I mean, like, the whole axiomatic quantum field theory is has. I mean, those guys have spent their life trying to precisely prove this, that this weak rotation makes sense. It is the main point about that is to just show that when you rotate the contour by 90 degrees, you do not encounter any singularities in between which could spoil the rotation. Okay, so if you do not encounter any singularities, then by complex analysis, you know that the horizontal contour and vertical contour would give you the same result. Okay, so what you need to do is at the end of your computation, check that there are no singularities which are going to spoil this weak rotation. Okay,
Yeah.
most of the quantum field theory does not encounter this problem. Yes, you're saying something.
No, I was just saying okay. Yeah.
Yeah. So most of the cases, there is no problem. In fact, one can rigorously prove this. The place where the problem occurs is gravity. Okay. When you do quantum gravity, it is not completely clear that you would be able to rotate it back uh, unambiguously. Most of the formulations of quantum gravity are uh, based on this Euclidean formulation, but you know, people have their own doubts about this thing. Let's put it this way, that axiomatic field theory results haven't completely been made watertight when it comes to uh, Euclidean quantum gravity to Lorentzian quantum gravity as yet. Okay, to large extent things have worked out, but quantum gravity is a tough nut to crack. Actually, that is a problem. But you don't do dynamical gravity. I think in most of the cases this problem is kind of taken care of. Okay.
Yeah.
And entire quantum field theory 2 is actually based, although nobody who will be teaching quantum field theory 2 would be getting into this worry, this issue of whether this weak rotation makes sense or not, because that would drive the course in totally different direction. That would require like probably 2 semester long discussion of axiomatic quantum field theory. Not really worth it, but anybody can actually look at it. Uh, Okay, for example, Bogoleba has a book, like 400-page book, just trying to explain these kind of points. Anyway, let's get back to what we were doing. So, so what I was saying was that, like, you get some matrix which tells you how to relate the vector that you started off with to the vector which came back after uh, parallel transport along a closed loop, and that matrix should be a matrix belonging to the local Lorentz group, and um, to, and it could belong to the entire local Lorentz group for arbitrary paths, or it may belong to a subgroup of a Lorentz group. Okay, and there are some interesting things that can happen with it. Okay, now of course we could ask a question, which is a kind of simple exercise, that you could ask what happens to a tangent curve vector to a curve. Okay, and what happens if you parallel transport a tangent vector to a curve. Okay, so far we parallel transported some arbitrary vector v alpha. You could ask what happens if that v alpha was a tangent vector. Okay, so that would be a kind of simple exercise. Okay, so the other thing is that the parallel transport is reversible. That means if you could parallel transport a vector from point x1 to x2, okay, so if v alpha x1 goes to w beta x2, okay, along using the parallel transport propagator p alpha beta, then you could kind of bring w beta x2 back to v alpha x1 by using the inverse of this propagator. Okay, and inverse of this propagator is the same as this propagator, but along the negative of the curve. That means you draw a curve from x1 to x2. Okay, and negative of the curve is the same curve but traced back from x2 to x1. Okay, that's what one means by minus c. Okay, So, so, so the reversibility just tells you that the parallel propagator is invertible. Okay, and one can actually show that the parallel propagator is invertible if the metric is non-degenerate. Okay, fine. So let's now take two curves going from x1 to x2. Okay, and let v be a vector defined at x1. Okay, so I have kind of deliberately chosen it to be a tangent to the curve c1 at x1. Okay, and we want to parallel transport this vector along c1 as well as we want to parallel transport it along c2. Okay, so what I've done is I have parallel transported it along c1, holding it to be constant, and brought it to a point x2, and that gives me w1. And I have parallel transported it along c2, holding it constant, because that's what parallel transport means, and it gives me w2. Okay, so these are the two vectors that I get by following two different paths. Okay, fine. So we want to ask a question: is w1 equal to w2? Okay, both these vectors are defined at x2. Okay, and question is that you started off with a single vector but parallelly transported to a new point x2 along two different curves. Okay, so in other words, remember parallel transport is done by parallel propagator. So you want to ask a question that is the parallel propagator from x1 to x2 along c1, is that equal, so that's a question mark, is that equal to the parallel propagator from x1 to x2 but along c2? Okay, they are equivalent questions. Is that okay? We could also ask one more question which is also equivalent. Okay, and that is uh, what if we take the vector v from x1 to x2 along c1 and bring it back to x1 along minus c2. Remember, as I mentioned, that it's an ordering issue. So you take the vector, transport it along c1. So I should have actually drawn arrow on this path pointing this way, and this path also pointing the same way. But I couldn't do it. It looked a bit tricky to me. So I just left it at this point. But like, mm, so so you assume that this path is defined with the arrow this way. It goes from x1 to x2. And this path is also defined the arrow pointing towards x2. Okay, so both of them are like that. So what we want to do now is to take the vector, transport it along c1 along the way the path is defined to this point, which is x2, but then now transport it back along minus c2. Why? Because it is going from x2 to x1. Okay, c2 is defined from x1 to x2, but we want to go back. Okay, so you define it this way. Okay, so that is the transport along minus c2. So we want to ask a question that what if I bring the vector back, is w obtained, which is something I have not drawn there, but whatever w you obtain, is that same as v? Okay, which is equivalent to a question that if I define a parallel propagator which goes from x1 to x1 but along a curve which is c1 minus c2, so you go along c1 to x2 and come along minus c2 back to x1, is this parallel propagator equal to 1? Okay, all these questions are identical. If this is 1, then this statement is true. Okay, and that statement also corresponds to w1 is equal to w2 because these propagators would be related to each other. Okay, is that fine? So of course we have used the reversibility of the parallel transport to write this expression in this particular form. Okay, Okay, so as I said, that if the answer to the first question was affirmative, then so would be the answer to the second question. So if the two vectors were same, then if you bring them back in the loop, then v mu and w mu also would be equal. Okay, fine. So now remember, we know that the parallel transport equation, which I can show you, it's this actually. Where A is minus gamma times the tangent vector piece. Okay, maybe it doesn't matter. I think I can just leave it at this point. There is a gamma involved in the definition of A. Okay, so a parallel transport equation involves the Riemann-Christoffel connection. Okay, and but we know that Riemann-Christoffel connection is not a tensor. Okay, and therefore it does not carry a invariant information about the space-time. Okay, in particular, you can just choose a coordinate system locally to set that to 0. Okay, and therefore it may not carry any information. In fact, it does not carry any information by itself about the curvature of space-time. Okay, so but we want to know that whether the parallel transport would know information about the curvature of space-time. And to figure that out, we don't really have to look at a large loop, or I mean, you don't have to take x1 and x2 far too away from each other, but we could just look at an infinitesimally small loop, closed loop, and ask the same question. Okay, so what we'll do is we'll just look at a small loop and ask, what if I parallel transport a vector? Okay, can I get information about the curvature of space-time, and how is that related to the parallel transport of the vectors? Okay, and because we know that curvature of space-time is 0 if I'm looking at flat Euclidean space, and in that case I know how to globally parallelly transport vector, because in fact the tangent space defined at this at one point is same as the tangent space defined at the other point. Okay, unlike in the curved space. Okay. Excuse me. Okay, so let's define lambda, which would parameterize a closed path uh, which starts at x alpha, which is defined at lambda equals 0, which is x0 alpha, and at lambda equals epsilon, which is a small uh, quantity. Okay, we want to look at an infinitesimal loop. Okay, uh, and x alpha at lambda equals epsilon is also same value. That's what we mean by closed loop. Okay, and I could have still parameterized that as lambda equals 0 to lambda equals 1 really, but the reason to do it this way is to kind of emphasize the point that the circumference of the closed loop could be just measured in terms of the parameter lambda that I want to use. Okay, uh, which is not even necessary. I mean, one could define the circumference to be epsilon times lambda, and lambda could go from 0 to 1. Okay, but anyway, so that is what is the way we want to define the closed loop. Okay, and suppose the vector v mu at lambda equals 0 is v0 mu. Okay, then we want to compute what is the difference when I bring the vector back along the closed loop and the original vector. Okay, and we want to compute up to order lambda square. Okay, right? Okay, so when we try to solve this up to order lambda square, it will basically give us a solution to this equation. Okay, we can check that we would be doing getting this answer, but in a perturbative fashion. Okay, order by order in lambda in some sense. Okay, fine. So what we'll do is we'll use the following form of the solution. We write down v mu to be v0 mu minus gamma mu nu sigma defined at x naught times v0 nu times x sigma minus x naught sigma. Okay, so notice that this equation is written in this particular form with a V0 nu written out here, because I'm trying to do it in a perturbative fashion. I should have written down V mu completely, because that is like the full parallel transport equation. But to leading order, this quantity would be same as this quantity, okay, because the correction would be at higher order. Okay, fine. So now what we'll do is we'll take this solution and plug it back into the equation. Excuse me. Okay, so let's first look at what happens to gamma. So gamma defined at x can be kind of Taylor expanded around x naught by gamma defined at x naught plus the derivative of gamma times x minus x naught to the rho, okay, which is same as x to the rho minus x naught to sorry x rho minus x naught rho, not the power. Okay, so so we'll use this fact to kind of write down this expression in a little clearer fashion. Okay, so here's the structure. So dv by d lambda is written in this particular fashion. I write down gamma x in terms of its Taylor expansion around x naught, and v of x with its solution. Okay, remember solution was written like this. Okay, so we just substitute this solution back in. Okay, so first one was the leading order expression where right hand side was v naught. This is the next order equation. Left hand side is the vector v that we want to determine. Right hand side is the corrected vector v. Okay, so it was initially only v naught. Now it is v naught plus gamma times v naught. Okay, is this okay? Is the procedure clear? Let me just kind of go down on the. Is the procedure clear? I just want to know.
Yes, sir.
Okay, okay, so good. So we are basically doing perturbative solution. This is a leading order form from which we got this kind of expression. Then we substitute that on the right hand side and we get this equation now. Okay, good. So all we have to do is to just expand this expression and step by step look at the terms. Okay, so first term that you get is gamma mu nu sigma multiplying v0 times dx sigma by d lambda, which is this term. Okay, there's a minus sign outside. The second term that you get is a derivative of gamma multiplying v sigma times dx by d lambda, which is that term. Okay. After that, what you get are the terms which involve two gammas or kind of term or derivative of gamma. Of course, derivative of gamma already we have encountered once. Okay. Fine. So now you get a term which is yeah. There's a small typo. I think I should have written down x minus x naught to the rho here. Okay, that piece is missing. I'll correct it. Okay. So next term is this gamma multiplies this gamma times v naught piece, which is a term like that, x minus x naught to the beta times dx sigma by d lambda. Okay, plus other terms. Okay, the other terms of course would require ellipsis here as well as ellipsis there, but we are not looking at the terms to that order anyway. Okay, this was the first order leading order piece, and this is the correction to that leading order piece. Okay, so now you can collect these pieces carefully, and you will find that you get a first term, which is a term written out here, minus gamma times v naught times dx by d sigma, which is precisely the term that you have it here, okay, at the leading order. Okay, then you get a correction, and the correction piece is a term here with the x minus x naught piece missing, but assume that it is there. Okay, that piece minus a piece which is gamma gamma, which also involves x minus x naught piece. Okay, so this del gamma and a gamma gamma piece is multiplied by v naught times dx by d lambda times x minus x naught, which is this piece. Okay, plus ellipses, which are all higher order terms which are not which are not our concern at this order. Okay, fine. Now notice one thing, that this piece was of course the leading order piece, but the next piece is a piece which involves derivative of gamma and a gamma gamma piece. This is something we have already encountered in the definition of Riemann tensor. Okay, except the fact that this quantity is in the case of Riemann tensor is antisymmetric in rho and sigma, and so is this uh, gamma gamma product, which is antisymmetric in rho and sigma, whereas you don't see it here. Okay, well, what you could do is to kind of write down this quantity as half of del rho of gamma mu nu sigma plus half of del rho of gamma mu nu sigma, doing nothing. Okay, and now you use the fact that rho and sigma is antisymmetrized and write down the second term as minus del sigma of gamma mu nu rho by swapping the indices. Okay, if you do that thing, that would tell you that this quantity would be just half the Riemann tensor. Okay, so that's what we will do. We'll write down this expression as half the Riemann tensor. Now remember that, like I told you, that you can write down del rho of gamma is equal to half del rho of gamma plus half del rho of gamma, and then you do a rho and sigma swap. Okay, uh, and flip the sign. While you are doing that, you will of course get a rho and sigma swap here also. Okay, and it may appear that that may spoil this relation, but that's not true, because rho and sigma are dummy indices and you can kind of call them whatever you want. Okay, so therefore in principle they could have been swapped and you get this expression. Upshot of this is that this quantity is just half the Riemann tensor. Okay, fine. So now we can ask a question: how do you solve this equation? Okay, and you find that this equation is solved by V naught minus gamma times V naught, which is the equation to the, these are the leading order solution, this is the first order corrected solution, and this is the second order corrected solution. Okay, so you take this as a, oh, this should have been capital V, sorry. So you take this as a solution now and plug it back in. Okay, and check what it would give. Okay, fine. So to this order, this equation would be solved by V mu is equal to a solution like that. Okay, of which this is a leading order solution and this is a first subleading correction to that, which we have already shown that it works. Okay, fine. So now what we could do is we can use this solution and put it back in the equation that we had, namely V mu at lambda equals epsilon minus V mu at lambda equals 0. Remember, both the vectors are defined at the same point, because lambda equals epsilon was same as lambda equals 0, because epsilon was the circumference of that closed loop. Okay, well, V mu of lambda equals 0, we know what it is. That is just V0 mu. Okay, so if you do that, then if you and V mu at lambda equals epsilon is this quantity. Okay, you can just take that and plug it in. Okay, it cancels the leading piece, and what you'll land up with is a term which involves gamma times V naught minus half of the Riemann tensor times V naught times this integral. Okay, is that fine? So of course you need to check that this piece would solve this equation, okay, up to this order. Okay, there will be a correction to order x minus x naught squared. Okay, by squared I mean x minus x naught to the rho times x minus x naught to the sigma kind of term. Okay, but to that order we are not solving this equation anyway. Okay, this is how the perturbative solutions are obtained. Okay, so what we get is this. Fine, is this okay? Okay, so let's do the next step, and the next step is to basically work in a coordinate system locally, of course, because both the vectors are defined at the same point. Work in a coordinate system in which gamma is 0. Okay, So if you work in a coordinate system in which gamma is 0, then the first term just goes away. Okay. So what you will end up with is V mu at lambda equals epsilon minus V mu at lambda equals 0 is given by minus half times the Riemann tensor times V0 times this quantity. Okay. Now, of course, the Riemann tensor is antisymmetric in rho and sigma. Okay. But so is this quantity. Okay. It is not immediately obvious that it is antisymmetric, but you can use integration by parts and take this derivative onto x minus x naught to quantity, and then you will find x minus x naught rho would have a, when the derivative acts on that, would have a minus sign due to integration by parts. Okay. So therefore this quantity is also antisymmetric. So therefore there is no contradiction in writing an antisymmetric piece here with this integral. Okay. Good. So we could formally, of course, write down x minus x naught to the sigma, which is same as a dx sigma by deta after all, because x naught is just a constant quantity sitting around. Okay, fine. So we want to ask a question: what is this integral? Okay, and this integral is not zero in general. Okay, so to see that, let's do the following thing. Okay, so let's consider a rectangular loop in x1 x2 plane. Okay, so I have drawn it here. Okay, and now you compute the x1 dx2 by d tau integral, okay, which is the same as this quantity that we are trying to integrate. Okay, one is the x1 direction, this is the x2 direction. We have just picked what rho and sigma are because we are kind of sitting in the x1 x2 plane. Okay, so that is the quantity, and we go from 0 to a to 0 0 to a0 to ab to 0b, and 0b back to 0 0. That is the loop. Okay, so you can do this integral, break that into 4 pieces. Okay, and we want to compute this integral by piecemeal computing these quantities. Okay, now of these things you can easily see that the first integral and the third integral would vanish, simply because you are doing the infinitesimal x2 element, but the x2 value is fixed. X2 value is fixed to be 0 here, and x2 value is fixed to be b here. Okay, so therefore these two integrals are not going to contribute simply because dx2 is just 0. Okay, so therefore in spite of having 4 terms in the integral, 2 of them just don't contribute. Okay, in fact the fourth term also is not going to contribute, because although x2 varies from b to 0, x1 is 0. Okay, all along the curve. Okay, so if x1 is 0 all along the curve, then this integral is just 0. Okay, so therefore what you find is that the first, third and fourth, all 3 pieces just vanish. Okay, so that leaves us with this integral being equal to the second piece of this integral. Okay, and in the second piece x1 is actually just constant a all along the curve. Okay, since x1 is a fixed value, you can just pull it out, and then you have to do dx2 from 0 to b. That just gives you the answer b. So the answer to this entire integration is a times b, and that whole thing comes only from this path. Okay, all other paths just vanish. But a times b is actually the area of this rectangle, right? Because rectangle with length a in one direction and length b in the other direction is just a times b. Okay, is that fine? So this is what I was saying here, that you are reduced to this, and therefore dx x1 dx2 by d tau integral along the closed loop is just the area of that curve. Okay, so in general this contribution is non-vanishing. Okay, and so because, and since this contribution is non-vanishing, you go back to the solution, you find that this integral is non-zero. V0 nu is typically non-zero. Okay, so therefore whatever is this quantity, okay, difference between the original vector and parallel transported vector, okay, is generically non-vanishing, okay, when the Riemann tensor is non-trivial. Okay, so I think that is the conclusion that we draw today, that because this quantity is proportional to area of the loop, okay, the parallel transport along a small loop gives us the original vector back only when the Riemann tensor is 0. Okay, there is no other term in our expression which would have given us the vector back. Okay, else we would have non-trivial effect. Okay, so what we find is that the parallel transport along the closed loop, okay, depends on the curvature of space-time. Why? Because the Riemann tensor carries that information. Okay, so I think I'll stop at this point today. Any questions? Hello?
Yes, sir.
Yeah, I was just wondering whether I was connected at all.